Hello everyone, welcome to Chapter 5, Integration, and the focus here is the fundamental theorem of calculus. Well, as the name says, this is really crucial in this portion of calculus where we try to make a connection between the derivation and the integration. The two concepts, the two pillars of calculus is kind of brought in connection here in the fundamental theorem of calculus. And this theorem has two parts, and I'll explain through them and try to give you a geometric proof for this, so you have an appreciation of how these two are connected. Here is part 1 of the theorem. If f is continuous on AB, closed interval, and capital F of x is integral a to x f of t dt is continuous on AB and differentiable on the interior of AB, and its derivative is f of x, small f of x, then we say f prime of capital F prime of x is d over dx integral a to x f of t dt, which is the same as f of x. Okay, a quick understanding of this. I know it's so concise that it can be confusing. Okay, now here's a play of notation, so I want you to track along with me. Now the capital F, is the antiderivative, right? Capital F is the notation we use for antiderivative, and antiderivative is nothing but your integration, right? It's a collection. That's a new notation we use. So if capital F of x is the integration, then if we took the derivative of the integration, right, that is what this means. Integration is f of x and the derivative, so f prime of x, and which is indicated here, d over dx. You take the derivative of the integral. It's as if the derivative and the integral cancelled off each other's effects, giving us the original function f of x. Okay, so to put it, really very bluntly, you can simply say this implies derivative and integral undo each other. And that's kind of what we see here. An integral undo each other, right? In terms of notation, symbol. So the prime notation and the integral. So here is the geometric proof for this. It's just for you to have an appreciation. I don't expect you to be tested on the proof itself. It's always good to insert the proof whenever we can. And so, in fact, this will kind of help you when you move to Calculus 2 to use this kind of thinking. Okay, let's say this was your function, and then let's say from A to B. Okay, and this was y equals f of t. I'm trying to use this f of t notation. It's t-axis and y-axis here, okay, because we do have x's coming in, so we don't want too many of these x's. So just for us to understand that if we were to find the area under the curve, then that will be the shaded region below the curve, right? So we'll come to that. So what we see here is integral a to x. I'm going back to the definition. Integral a to x f of t dt. That means the area under the curve f of t all the way from a to x. That's what it means. And that's what we learned in definite integral. So I'm going to write that information here quickly as a little aside for us. Integral a to x f of t dt implies it is a definite integral, right? Because you have a definite start and an end point for this integral. But more importantly, the interpretation of this is area under the curve y equals f of t, right? F of t is what we have here, from a to x. That's what this means. Therefore, when I come back to my graph, I start at A, and x is somewhere in between, right? So not exactly in the middle, but somewhere between, before B, because the whole focus is between A and B. And so this is the area under the curve, isn't it? So this is integral a to x f of t dt. And we are calling that as our capital F of x. That's our area, right? And so we want to show that if you took the derivative of this area, you will get back this function, this orange curve. Okay. So now to illustrate that, let's go back to what we know about capital F prime of x. If it's capital F prime of x, we know from the difference quotient idea, right? Limit of difference quotient. It'll be whatever this function is. Here it's capital F. It's small f, we'll use small f, right? So capital F of x plus h minus f of x all over h. Again, remember, this is the definition. The power rule, chain rule, all those are techniques to help us do this derivative quickly, but this is the definition. So I fall back on the definition here. So what this means is, if I chose another position x plus h, right? Yeah. If this is x plus h, I'm sorry. Now what we have though is the area under the curve for x plus h would be this whole thing. Do you agree with me? Everything to the left of x plus h. So the purple one is extending all the way to x plus h, while the pink one stops at x, isn't it? So so let me write over here, f of x plus h is the area to the left of x plus h, and f of x is the area to the left of x. So when we say capital F of x plus h minus capital F of x, then it means that we're only talking about this portion in between the two, right? The x and the x plus h. So that is all we are interested in. So if it is this portion, right? For this portion, I want to kind of show that out here for you. And you had the graph coming down like this, right? And this was x and this was x plus h. So correspondingly, this point will be f of x and this will be f of x plus h. These are the points, the height, right? The height here. So this one and this one. Okay, so we have that. So what we're trying to see here is, we can see that this is roughly a rectangle, right? A rectangular shape. So if this is a rectangular shape, this difference, let me write that out here, f of x plus h minus capital F of x. This difference is approximately equal to the green rectangle. Area, because there's a difference of areas, right? So this green area would be roughly this rectangle. So if you're talking about the rectangle, then you can think of the area of the rectangle as length times the width, or in this case, the length could be this height, which is f of x, and this distance is your width. So x to x plus h, which means the difference was h. So it's the same as h times f of x. This is approximately h times f of x, right? So if we divide both sides by h, we get f of x plus h minus f of x all over h to be approximately equal to f of x. And therefore, when we now apply the limit, okay, as h approaches 0. And here you don't have any h, right? So the limit does not have an effect on the right hand side. So this is equal to your because you apply the limit now, you're removing the h. This will be equal to f of x. Right? But we do know that limit of f of x plus h minus f of x over h is f prime of x. Oops. This implies f prime of x is equal to f of x. And that is what the x properly. And that is what the fundamental theorem of calculus part 1 tells us. It says f prime of x is the same as f of x. It's as if you took the the derivative of the area, which gave us the function. It's as if these two kind of cancelled off, right? Left us with just the area. So the proof for this theorem is a geometric approach where we fall back on the definition of derivative, but using that definition here in terms of understanding it as the area, because you're taking the derivative of capital F, and capital F indicates the antiderivative, and that is why you have that effect of one undoing the other. So this implies derivative of an integral gives back the function curve. Yeah. Okay, so that is, we'll do a couple of problems here just to understand how it plays out in problems, and then we'll go on to part 2. Use the fundamental theorem to find dy over dx if problem 1 is y equals a to x integral a to x t cubed plus 1 dt. We are asked to find dy over dt using the fundamental theorem. So take the derivative. So that's going to be dy over dx. That's what they want. The variable of integration is t. Okay, but remember the theorem looks like that too. So dy over dx is what we're trying to find. So I'll say dy over dx integral a to x t cubed plus 1 dt. Let's take a quick look at the definition. The definition says d over dx. I should have removed the y because we replaced the y by this. So d over dx integral a to x f of t dt returns f of x. Okay. So, apologize for that part. It should be just d over dx because y is this entire thing. We know that this thing is like your f of t, right? Basically it's your f of t. F of t is t cubed plus 1. So then we know that this returns by fundamental theorem f of x. I'll put FTC, fundamental theorem of calculus, part 1, right? So from that we know that this is directly equal to f of x. So if f of t is t cubed plus 1, f of x must be, in the place of t you replace it with x, so it's going to be x cubed plus 1. So dy over dx is simply x cubed plus 1, because it's as if the derivative and the integral undid each other and gave us the function in terms of x. The same instruction, but let's go to problem number 2, where y equals integral x to 5 3t sine t dt. So dy over dx will be d over dx, and y is this, right? Integral x to 5 3t sine t dt. It looks fine except for one part where your fundamental theorem of calculus says it should go from a to x, not x to some number a, right? In this case a is 5. But we do know that from the order of integration, from the set of rules we saw before, We can switch this order if we throw in a minus. So if I make it a minus, then the integral can be switched from 5 to x, 3t sine t dt. The minus can be brought out of this entire show and left outside the whole action. So that shouldn't impact us. This is your f of t. So f of t is 3t sine t. Put the t properly there. That's going to be negative d over dx integral 5 to x 3t sine t dt. That's going to be negative f of t. F of t is 3t sine t, but the formula says it's f of x. So in the place of t, we plug in x. So that's going to be 3x sine x with a negative. The third problem is y equals 1 to x squared cosine t dt. Okay, now we could work the same way if it was 1 to x, but remember here the problem is giving us 1 to x squared. Okay, so we want integral 1 to x, not integral 1 to x squared. So when you have those situations where it doesn't match the format, we have to use substitution. So let u be equal to x squared. Okay. This implies we use chain rule. The reason is because we need to get dy over dx, but you have to go through the u. Okay. So you get to the x through the u. So dy over dx will actually be dy over du times du over dx. Remember the chain rule? Because of the substitution, you have one layer to insert. And that means we'll take the derivative with respect to u, not with respect to x as we did before, because you are replacing your x squared with a u. Okay? Cosine t dt times du over dx. And we know here again, this is f of t. And therefore, according to Fundamental Theorem of Calculus Part 1, this would give us back an f of u. Okay. Du over dx. Are you with me on this? So this will be Fundamental Theorem of Calculus Part 1. Okay. Gives you this f of u, because it was with respect to u. If it was dy over dx, then this will be f of x. So it's always it's with respect to what we derive that will come in here as per the theorem. And f of u, f of t is cosine t, so f of u will be cosine u times du over dx. Alright, now it's time to get everything in terms of x. So u will be x squared, and du over dx, u is x squared, so derivative of u will be 2x, right? So then we got our dy over dx to be 2x cosine x squared. We did use the fundamental theorem of calculus, but because of the fact that it didn't match the format, we had to use substitution. So we took a little detour. It was a short detour where we introduced the u substitution, and then were able to overcome the limitations, and then now we were able to rewrite the answer back in x, and that's our derivative. We'll do another one. 1 plus 3x squared to 4, that's the integral. 1 over 2 plus t dt. It does look a little complicated, don't worry. So this is d over dx of y. So this is our integral. Okay. Now remember again, we have to go from a to x, not x to a. So we have to switch the order of the integration. So in order to switch the order, remember I'm bringing out the negative because I anticipate it to happen here. So I'll just bring that out. So that's going to be integral 4 to 1 plus 3x squared 1 over 2 plus t dt. What's really neat is you're able to switch the limits of integration, not affect the function itself. And of course you do have a minus. Now we want integral 4 to x, a to x. So a here is 4, which is fine, but not integral 4 to 1 plus 3x squared. So because we do not want that, once again, we use the substitution. U equals 1 plus 3x squared. We'll quickly do the du over dx because we know we'll need it in the end. That's going to be 6x. And once again, we use the chain rule. So we go from y to x through the u. So dy over dx will be dy over du times du over dx. So dy over dx will be d over du of this y. And y is integral 4 to 1 plus 3x squared, but 1 plus 3x squared will now be u. So we're going to go from 4 to u, 1 over 2 plus t dt times du over dx. And this whole thing is Fundamental Theorem of Calculus Part 1, and f of t is 1 over 2 plus t from there. Right? Therefore, Fundamental Theorem of Calculus tells us that this will return f of u, and then you have the du over dx. Okay. Now, in all this action, there's one thing I forgot to insert, which was the minus. Right? Remember, there was this minus in this whole action. So I'm just going to bring that back here. In our case, we have that minus to tag along. Okay, minus, that's better. 1 over 2 plus u, right? It's 1 over 2 plus t. In the place of t, I plug in u. And du over dx, we found that to be 6x. Now replace all your u's with the original x. So 2 plus u is 1 plus 3x squared times 6x. Clean that up. That's negative 6x on the top. Over 2 plus 1, 3. 3 plus 3x squared. You can factor out a 3 in the bottom. Don't just cancel them as they are. You always have to factor out, because you can only cancel if they were in the product format. And so that will give you 2 there, which in turn is negative 2x over 1 plus x squared. This is your dy over dx using the Fundamental Theorem of Calculus. So I hope you were able to see the application of this theorem in these 4 problems, and especially in problems that do not match the format we want. Sometimes the order of integration is what we need to change. Sometimes it's just one of the limits of integration that we need to use the u substitution. Or like in this last problem, you might have to do both, where you adjust the order of integration as well as the limit of integration. Now we move on to part 2 of the theorem. If f is continuous over closed interval ab and capital F is any antiderivative of small f, the function on ab, then integral a to b f of x dx is capital F of b minus capital F of a. Okay. So this is really cool. This is also known as the Evaluation Theorem. So let me write that maybe here. That's another name for it, because you're kind of evaluating the limits of integration, the a and the b. Okay. So integral of f of x is the area under the curve, which is your capital F. And so what you're saying, well, if it was just integral f of x, the indefinite integral, right? You simply called it capital F of x. But now when you have a and b inserted into this, we're saying this would become f of b minus f of a. It does make sense because you are taking the integral of f of x from a to b. So if you had the curve a to b, right, we're saying the integral under the curve up to b, right, minus the integral of the curve, integral under the curve up to a. You take the difference of those two, and that's what you get, this area here in between them. So it is the area to the left of b minus the area to the left of a that gives you the area in between a and b. So let me write that down here. Area to the left of b minus area to the left of a, that gives you area between a and b, and that's what we mean by the definite integral. Integral a to b f of x dx is the area from a to b under the curve, which is this shaded region. Okay. So how do we put the two parts together? So if I were to explain FTC1 and FTC2 together, what do they mean? Because there was a reason why we split them into two parts, so that you can see them from two different angles. Now it's time for me to bring them together, and that would mean that the area under the curve over a to x, not a to b, right? A to x is a of x integral capital A of x, right? We usually use capital F of x, but because I'm talking in terms of area, I'm just using capital A. You can easily replace it with capital F. So it's a to x f of t dt, right? That was from FTC1. So it said if you took the derivative of this area, we got back our function f of x. So what you saw as capital F, which is a notation, now we are trying to see it as area, which is more practical, right? So this implies that FTC1 says derivative and integral undo each other. We saw this already. And FTC2 says area is the definite integral. Do you see that? So the area is the definite integral from a to x, or if it was defined from a to b, then we've got that area under the curve. And so for a to b, we did f of b minus f of a. So area of, if I use the a notation, and if I saw the capital F as area, then it's the area. I can quickly take you back here. So see here, capital F is written in terms of area. So it's the area to the left of b. So integration, definite integral, is basically your area. And so area to the left of b minus area to the left of a. And that's what it means here in terms of fundamental theorem of calculus, where we have the connection between the derivative and the integral, and the connection between the area and the integral. So if I were to expand this a little bit, okay, I did this graph before, maybe I should have kept that. Let's say it's going from a to b. Okay, a to b. I'll use a different color for this perhaps. Okay, so to get this area, I need to get, so let's say it's from 0, right? That's a common reference. So area under the curve a to b f of x dx. This is f of x. So fundamental theorem of calculus 2 says this is the same as area f of b minus f of a, isn't it? But if you think of it, it's nothing but integral 0 to b, right? Area to the left of b. So it goes all the way up to 0 to b f of x dx minus integral 0 to a. So this whole thing minus this whole thing gives you in between a and b. So this is 0 to a f of x dx. And that is how we understand the integral and the area being connected. Okay. So in terms of notation though, when we do it in problems, okay, integral a to b f of x dx will be written like this: capital F of x, and there is like a bracket, or sometimes they even use this kind of just a vertical bar, okay, and they write a to b. What this means is, because it's known as the evaluation theorem, you basically evaluate the function capital F of x for b first, because that's the larger area, minus f of a, which is the lower limit of integration. That will give you the smaller area. You can see that visually too here. But that is a quick notation. So we will be using this evaluation notation. Okay. So that will help us to use the theorem in this kind of notation as well. So let's check it out in the following problems. The problem instruction says calculate the definite integrals using evaluation theorem rather than by taking limits of Riemann sums. So I want to quickly pause here before I reveal the question itself. Is that if you recall Riemann sum, we did we were given a to b, right, the closed interval, and we took the area under the curve and divided them into very thin rectangles, and we were usually instructed to use either the lower sum, the lower estimate, or the upper estimate, and if they didn't instruct us, we were allowed to choose any one, and we did it using the Riemann sum, which was the limit of the areas, right? The limit of the sum of the areas of these rectangles. So that, as you know, was quite cumbersome for us to do. So they're saying don't do that, rather use evaluation theorem, because it's going to make it so much easier. Okay. So here's the first problem. Integral 0 to pi cosine x dx. So I'll say, remember, evaluation theorem is another name for FTC2, part 2, right? FTC part 2. So this implies we will do integrals using reverse of derivatives. So in other words, it implies that d over dx of sine x, right, gives us cosine x, isn't it? Yeah. So derivative of sine x gives us cosine x. We're asked to find the integral of cosine x dx. So integral 0 to pi cosine x dx equals, let me quickly recall FTC. FTC said integral a to b small f of x dx is capital F of x at evaluated from a to b. Okay, that's the other notation I showed you. So capital F of x is already the integral of the small f of x. So in other words, it is the antiderivative, isn't it? The antiderivative. So we're asked to find the antiderivative of cosine x, and we can do that by using the reverse of it, right? So if you took the derivative of what function will give me cosine x is the actual question, right? Antiderivative of cosine x is same as figuring out the derivative of what will give me cosine x. You can fall back on the formulas we saw, definitely, but this is a quick way to recall and make a connection with all of these. And we know that that's going to be, I'll use the other color, it's going to be sine x That's your capital F of x, evaluated from 0 to pi. You can also use this single bracket notation. And we know it is sine of, in the place of x you substitute, you evaluate the upper limit of integration minus sine of the lower limit of integration. Sine pi is 0 minus sine 0 is also 0, which is 0. So technically, the integral from 0 to pi cosine x dx gave us 0. Okay. And I'm going to shortly explain to you why that is the case. Okay. I mean, what does this mean? This means that the area is 0, isn't it? Yeah. Because this is nothing but area under the curve of cosine x from 0 to pi comes out as 0. But we know that cosine function is a wave graph, which means 0 to pi, you do have some movement of the graph, so there should be some area. Why is it 0? Think about it. We'll get back to it shortly. There is a reason why it shows up as 0. Meanwhile, let's just focus on just the evaluation theorem here. And so the next question is given to be this. And we know that, integral of secant x tan x is secant x itself. So you can see it two ways, okay? So this implies integral, just the integral, I'm not talking about the definite integral, is secant x. Or if you went back to derivatives, right? If you went back to derivatives, secant x tan x was the result if you took the derivative of secant x, right? So they must be the same, right? Because one is the reverse of the other. So you're basically reversing the process. All right, either ways, we know that the integral of secant x tan x is secant x. So this implies integral negative pi over 4 to 0 secant x tan x dx is this capital F of x. In this case, it's secant x evaluated from negative pi over 4 to 0. So now we evaluate it from upper limit minus the lower limit. And remember, the lower limit has a negative. There's a negative in the problem and the formula. There's a negative in the substitution, so watch out for that. Secant of 0. Remember, there is, if you looked at the number, the unit circle, you won't see the secant directly, but you know secant is the reciprocal function of cosine. And therefore, cosine 0 is 1 and its reciprocal is 1 minus. And you also recall that cosine is an even function, which means it absorbs the negative. And its reciprocal function also absorbs the negative. So it's as if you had, it's as if there was no minus. So it's like same as secant pi over 4. And secant pi over 4, if you look at cosine pi over 4, that will be root 2 over 2. And you need to take the reciprocal of that. So 1 minus 2 over root 2. If you simplify this, it gives you 1 minus root 2, right? You can rewrite the 2 as root 2 times root 2. So that one of the root 2's will cancel off. So you have 1 minus root 2. And that's the answer there. We'll go for the third one. Integral 1 to 4, 3 over 2, square root of x minus 4 over x squared, whole thing dx. Okay, so once again, you can think in terms of the reverse order, or you could use our integration rules, right? The integration rules were, forget about the 1 to 4 for the moment. I can split it up like this, isn't it? You can even keep the 4 outside and do 1 over x squared dx. So I could have done that here too. I'll pull out the 3 over 2 and just have the integral root x. And to kind of clean this up, so the x power half dx minus 4 integral x power negative 2 dx, and you know that's going to be x power half plus 1 over half plus 1, right? You'll have the plus c if you recall, right? You have the plus c. But because we do not have any confusion of any constant here, because the plus c, remember if what I mentioned was a collection of all antiderivatives, because there was no limits of integration. But here you have the limits of integration, and this is a good time for me to insert it. So if I bring in the limits of integration, there is no need for plus c. Okay, and then I move on to, there is this 3 over 2, this is missing, 3 over 2. I'll remove this plus c, minus once I take the integration, I have to enter the limits like this. Okay. Just for our convenience, I'm going to give this in a different color so it's easy for you not to get mixed up. 4, yeah. And then this is minus 4 x power negative 2 plus 1 over negative 2 plus 1. Once again, there is no plus c here, and so we can evaluate from 1 to 4. I know it's a little messy, but just work patiently through it. So this is 3 over 2 x power. Don't be in a hurry to evaluate yet, because we want to first take care of all the constants, get them out of the way, and then just for the x we'll have to substitute, because that's the only variable, right? So that's going to be 3 over 2 over 3 over 2 negative 1 over negative 1, and then I'll bring in the limits 1 to 4, 1 to 4. I'm still in the cleanup process, so this is 3 over 2 in the bottom. That's going to flip up and become 2 over 3. Just for convenience, I'm going to put it out all explicitly for you. So we are just left with x 3 over 2, and this minus will combine to give us a plus 4. X power negative 1 will be the same as 1 over x, right? And I just want to apply the limit for just the x part. Are you all with me on this? So the 3, 2's, all these go away. Again, I'm going to keep it in one more step. 1 to 4 plus 4 over x 1 to 4. I'm combining these two. Okay. Alright, so that is so much more manageable because I've removed all the clutter. Okay. So now for this, I have to do 4 power 3 over 2 minus 1 power 3 over 2. So let me put that, maybe I'll use curly brackets because we have the single bracket. So I'll do 4 power 3 over 2 minus 1 power 3 over 2, right? I evaluate the upper limit minus the lower limit, plus this one will be 4 over 4. In the place of x, you plug in 4 minus upper limit minus the lower limit. So 4 power 3 over 2, 4 power 3 over 2. You can use your calculator, but try to use algebra, mental math as much as possible. So what happens here is, this is square root of 4, the whole cube, isn't it? The 2, the bottom one is your root, the top one is your power. So square root of 4 is 2, 2 cubed is 8. So 8 minus 1 power anything is 1, so you got that, plus 4 over 4 is 1, minus 4. So that will be a 7 plus that will be negative 3, which is positive 4. So that is our answer for the third problem. So let me take you back here. We kind of forgot where we started. So the area under this curve from 1 to 4, this is a curve, right? So the area under this curve from 1 to 4 is 4. That's what this means. Okay. All right. Now we did these 3 problems, and the very first problem we got the answer as 0, and I told you how can it be 0? Can you think about it? So we applied the evaluation theorem and we got a 0, but you can't blindly apply these things, right? There should be some reasoning as to why that is. And that reasoning is upcoming now. What we have here is the net change theorem, and this is a very, very neat theorem because this basically integrates both the differentiation and the integration techniques here. And this is going to give us an explanation of why we got a 0 when we measured the area, when we found the integral of that cosine function, the first example, where the area came out to be 0. So we're going to build up to the understanding of what's happening with the net change and the total area and things like that. Okay. So let's read this theorem. The net change is a differentiable function capital F of x over an interval a to b is the integral of its rate of change. Okay, so f of b minus f of a is integral a to b f prime of x dx. Okay, this actually comes in the beginning. It comes from our evaluation theorem, which is FTC2, right? So that's integral a to b f of x dx. And so I'll say FTC2. But you know that this f of x dx was itself f prime of x from FTC1. FTC1 said capital derivative of capital F of x was small f of x. You can actually go back, pause the video and go back to it and reference it, or look at the ebook for a quick reference. So what that means is then I will replace my f of x with the capital F prime of x dx, and that is your net change theorem. So it's integral of the rate of change, because f prime of x, right, is the derivative, so it's the rate of change. So we do have some interpretation for this, and I want to show that in different contexts, like in economics, in physics. What does it mean? Okay. Let's take a quick look at that. Interpretations of net change theorem. So let's start with the first scenario where in economics we know that C of x indicates the cost of producing x units. We did that, right, previously. So I'm just trying to recall that. And if you recall, C prime of x, which in math we call as a derivative, but in economics it's known as the marginal cost. And there, this very net change theorem would be rewritten to go from x1 to x2, right? X units. So x1 units to x2 units. C prime of x dx would give cost of x2 of producing x2 units minus cost of producing x1 units. That's how they will interpret this. Yeah. Now the other scenario, say in physics, you know the velocity is the derivative of the position. Remember that? ds over dt. We're using the prime notation, so I want to stick to the prime notation. You know, velocity is the derivative of the position, right? Position. So when the position moves from one position to another position, that movement, that change in that position is known as a velocity. So if we were to do from time 1 to time 2, because that's the variable. So if we took the integral from t1 to t2 for this velocity of dt, you know that can be actually replaced, the v could be replaced by s prime of t dt, and that is coming from your net change theorem. That's the same as saying s of t2, the position of the object at time t2, minus the position of the object at time t1. So what this really means is you're talking about the displacement over displacement, right? Displacement is the movement from one place to another over the interval t1 to t2. That's the rate of change. So let me explain the concept of net signed area. We have the net change theorem, right? What does it mean? The theorem relates to the integration. So integral means the area. So it's better if we did it, if we try to understand this as area. Okay. So let's say you had this graph. Okay. I'll just stretch this a little bit here. So you have this area under the curve, and notice that the area goes above the horizontal line, below the horizontal line here, and once again above the horizontal line. So if I use the language net signed area, notice the word signed, it means that the area above the horizontal line will be positive, right? So A1 will be positive. The area above the horizontal line on this side is also positive, A3. But the area below will be negative, so it will be as if you had a minus A2. What we see here is that the definite integral, you remember definite integral is from integral A to B, right? The definite integral computes the net signed area, which means you don't just add the areas, you just add the areas, the positive areas, and you'll have to subtract the negative area. And so that is the reason why you have this area taken off, which means it's basically compromising on the area. You're not getting the full area. Therefore, we have to consider the total area. Right? If you wanted to find the total area for the same information above here, then I have to do A1 plus, take the absolute value of A2, because you know A2 is going to be negative, but if you took the absolute value, it will return a positive, and then A3. So this will give us a area must be positive for total area, because as the name says, total area, it doesn't matter if it's above the x-axis or below the x-axis. We just want the total area. Therefore, when we find the definite integral, we're going to have trouble because it's going to do the net signed area. So total area, we have to remember to take the absolute value of the function in order to get the positive area for all the portions that are either above or below the x-axis. I hope this got you thinking into seeing why we got 0 as the area for that cosine function. It's possible, in fact not possible, it's true that it was something like this. Let's say A1 and A2. Okay, so if A1 and A2 are the same, but they are, because one is above and one is below, we found the definite integral, and because it computes the net signed area, the area above and the area below kind of cancelled each other because of that minus for the negative area, and that gave us a net signed area to be 0. Okay, and so if we want to overcome that, we want to find the total area, then definite integral must have the absolute value in it to convert all the negative areas into positive areas. Here's the question. Find the graph of f of x equals sine x between x equals 0 and x equals 2 pi given below. And here's our graph for y f of x equals sine x. And they ask us to compute two parts. One, the definite integral of f of x over 0 to 2 pi all the way. Okay. And two, the area between the graph of f of x and the x-axis over 0 to 2 pi. Okay. So we have, let's start with part A. So in part A, for f of x equals sine x, and this was over 0 to 2 pi, integral 0 to 2 pi, f of x, let's put this f of x dx, that will be the same as integral 0 to 2 pi sine x dx, right? Because I was trying to just interpret the question as it said. The definite integral of f of x over 0 to 2 pi would be written like this, and you replace the f of x as sine x. And you know the integral of sine x is cosine x with a negative. That's coming from the formula, so go back to the formula. The ebook also has a table of derivatives and a table of integrals at the very end of the textbook as an appendix, so you can also cross-reference that for quick access to these formulas. And so well, we have this, and because it's definite integral, you don't have the plus c. Instead, you have limits of integration to substitute. So remember again, if you did not have these limits, it was always a plus c. We call that the indefinite integral. For the definite integral, you definitely know what the limits of integration are, the end points, and so we're going to evaluate them. That's going to be negative cosine 2 pi. If it confuses you, you can always put keep the negative outside and just focus on the cosine x. So cosine 2 pi minus cosine 0. Personally, this is what I like to do. I don't like to bring in the minus and then remember to change it to a plus later and so on. I'll rather separate it and only focus on the cosine x. Alright, so that's going to give me negative cosine 2 pi is a 1 minus cosine 0 is a 1. It comes out like a negative 0, which is 0. So the area we saw, it's showing us 0, but you can clearly see the yellow and the blue shaded region. So what do you think is happening? Again, if you recall, the definite integral gives the area 0 because it's computing the net signed area. So it's taking the area above the x-axis and it's subtracting the area below the x-axis, because the area above the x-axis gave us a nice number. This also gave us a nice number, but because they got minused, it's actually the same area up and down, which came out as a minus. Okay, so let me quickly note that down here and say the definite integral, which was part A, gives the area as 0 because it computes the net signed area. And we can see that visually that's true because the yellow area and the blue area are the same. When we do part B, we'll actually know what their areas are. So let's go ahead and do that, because part B says find the area between the graph of f of x and the x-axis over this. So technically they're asking for the total area. Okay, so let's go to part B. Total area would be add the areas by taking absolute value of the portion where area gets negative. A negative area does not make sense, but when we compute the indefinite integral, it is considering the direction, the placement of the area, and so it is doing the net signed area. But when we say total area, we want the total sum of the area irrespective of its placement, right? And if you go back again to the graph, we see that from 0 to pi the area is positive, from pi to 2 pi the area is negative. So if I did the absolute value for the pi to 2 pi just for the blue region, it's as if I flipped it over to the top, right? It'll be as if it flipped over to the top, and then that area is what you're computing. That's how it's going to appear. So it's got the two areas there. Okay, so that means I can use the properties of integrals, where if I want to go from 0 to 2 pi sine x dx, this is a definite integral, and we know this will give us a net signed area. So we're going to split up the area from 0 to pi sine x dx, we know this is the blue shaded region, plus absolute value of pi to 2 pi sine x dx. Okay. If you took the absolute value of that area, that will give you the yellow, no, that was a blue. So this was a yellow shaded region. So I'll just do this. And this was the blue shaded region. All right. Now we have the same, the integral of sine x is the same, negative cosine x. You just have different limits of integration to help you through that. So take the absolute value of negative cosine x. The limits of integration would be pi to 2 pi here within the absolute value. Okay. As always, separate the minus, and because there are too many brackets in this and that, let's use the curly brackets. Cosine pi minus cosine 0, okay, that, plus absolute value of negative cosine 2 pi minus cosine pi. Right? Write it very, very clearly. Don't try to do all these steps in your head. Put it out, write it down so you can retrace your steps. So we have negative cosine pi is negative 1 minus cosine 0 is 1 plus absolute value of negative cosine 2 pi is 1 minus cosine pi is a negative 1. Okay. Be super careful here. This is absolute value bars. Make sure that you, when there are double minus, watch out for that. So that's going to be negative of negative 1 is negative 2 plus absolute value of negative 1 minus of minus 1, which is 1 plus 1, which is 2. Negative of negative, this is positive 2 plus absolute value of negative 2 returns a positive 2. So 2 plus 2 is actually 4. So you can actually see that the area originally for the yellow shaded region was 2 and the area for the blue shaded region was also 2. But when we did the net signed area, which is the definite integral, we got this area 2, this was 2, and this was a 2, but we did 2 minus 2 and that gave us a 0. When we did the total area, we brought the area up above, so it's 2 plus 2, that gave us a 4. Steps to find the area. Now in the previous problem, we were able to draw the graph and go see that it went from 0 to pi as positive area and pi to 2 pi as negative area. Now this could be because the function was very convenient. It was a sine x, so we were able to see that. It's a standard function. But how do we do it if it was a any given function f of x? So we have these steps. The steps are that you'll first subdivide the area AB at the zeros of f, because at zeros, which are the x-intercepts basically, that's where the graph crosses the x-axis. So you know whether it's going up above the x-axis or below the x-axis to know if the area will be positive or negative. For that reason, you subdivide the area, the interval at the zeros. Step 2 is to take the integration of f over each of those subintervals. And step 3 is take the absolute value of each one of them and add them up. Now, this is to find the total area, right? If it's net signed area, then definite integral will do the trick for us. So there's no trouble, it's already inbuilt. But if we want to do this, we're saying just take the absolute value of every part. Even if it's a positive area, it doesn't matter, because it's still going to return a positive answer. But if it's a negative area, taking the absolute value will return a positive answer, making all the parts produce a positive area, and therefore you can add them up for the total area. So these are steps to find the total area. Okay. So here is our question. Find the area of the region between the x-axis and the graph. The description is for the area that you have to find. So it's between the x-axis and the graph. That's what it says. So f of x is x cubed minus x squared minus 2x negative 1 to 2. Okay, that's your interval. Usually they'll give you just this much information. You'll have to use your graphing calculator or figure out a way to graph this. Sketch the graph so that you have an idea of how it goes. Okay, so if you couldn't sketch the graph, we're saying these steps to find the area would still help us because we are approaching it algebraically and not visually. So for that sake, I am going to do this algebraically and then show you the graph in the end. Okay, so let's start with step 1. Okay, step 1 is to find the zeros. To find the zeros, you set your f of x to 0, right? That's the reason why it's actually called the 0. It's the x-intercept, so set your y to 0. All right, to factorize, factorization is the way to go. So pull out the x. The GCF here is x. You can pause the video and do the factorization yourself. There should be a minus. So you've got these 3. You have the degree as 3, so you should have 3 x values. So 3 zeros are 0, negative 1, and 2. All right. So we don't have a visual, but you can see that you're looking from negative 1 to 2, and you do have zeros occurring at the end points, and there is a 0 in between at 0. Okay. So step 2 says, let me go back, integrate f over each subinterval. So we are asked to do negative 1 to 2 f of x dx, right? But we know that this will produce net signed region, so we're breaking it up from negative 1 to 0. So here, if you look at my zeros, I've kind of arranged them. I didn't arrange them in any order. So if it helps you, you can rearrange them in ascending order so that negative 1, the smallest number from least to greatest. That way, you can kind of see how the intervals will split. It will split from negative 1 to 0 and then from 0 to 2. Okay. Now, because I anticipate these to be kind of lengthy, I'm going to do them in parts. So I'm just going to focus on negative 1 to 0 first for the first subinterval. And f of x was x cubed minus x squared minus 2x dx. You can take the integral individually, or you could simply just do all of them at once. So the x cubed will be 3 plus 1 over 3 plus 1. So that's going to be x power 4 over 4 minus 2 plus 1 over 2 plus 1, right? So that's going to be x cubed over 3 minus 2 times, that will be 1. The power is 1, so 1 plus 1 over 1 plus 1. So x squared over 2, and the limits of integration will be negative 1 to 0. I can actually cancel these the 2's off. That will make it a lot easier here. One more step. Okay, because we did them all together, you can evaluate all of them at 0 first and subtract and evaluate at negative 1. Okay, so this is when it's 0. So 0 power 4 over 4 minus 0 power 3 over 3 minus 0 squared, that. F of b minus f of a, remember that? So upper integral, upper limit minus the lower limit. That's negative 1. Please remember to put parentheses around negative 1 before you take the power. Because you'll see that because the powers are even and odd, it will begin to matter if we did not use the parentheses. Are you with me on this? Okay. So what this lets us see is that the first part will be 0. The whole thing is 0 on the top, minus 1 over 4, negative 1 power 4, 1 over 4. Now there's a minus here, and there will be a minus 1 power 3 will give us, the whole power 3 will give us a negative 1. That negative and this negative will become positive, so 1 over 3. Negative 1 the whole squared is positive, but you have a minus here, so negative and the positive would make it negative 1. Use your basic algebra to combine them all. You get 5 over 12 for the first subinterval. Now for the second subinterval, 0 to 2, f of x dx, which is 0 to 2 x cubed minus x squared minus 2x dx. And because we just did that, please try to simplify the steps as much as possible. That will give us x power 4 over 4 minus x cubed over 3 minus x squared, limits 0 to 2. Again, remember, it's not a plus c, because plus c is only for indefinite integrals. This is a definite integral, so no plus c. Instead, you will be evaluating at the limits of integration. Alright, so that's going to be 2 power 4 over 4. There was no sign, so I just put the 2, otherwise I'll put the parentheses. Minus the lower limit of integration. So that's going to be 2 power 4, 16 over 4, which is 4, minus 2 cubed is 8, that will be 8 over 3, minus 2 squared is 4. Okay, that's for the top one, minus all of these will be 0. Again, pause and compute it yourself. Well, this is kind of easy because the 4 and the negative 4 will cancel each other, so you get negative 8 over 3. Now notice that this area is giving us negative, so you can already imagine that when you sketch the graph for this, that this portion from 0 to 2, that portion of the graph will happen below the x-axis because the area is negative. Right? This portion is positive, so the first subinterval will be above it. So we got 1, 2. Then the third step is to add the absolute values of the integrals. So the third step is, third step is integral negative 1 to 2 f of x dx will be absolute value of 5 over 12, the first subinterval, plus the absolute value of the area from the second subinterval. Again, 5 over 12 was already positive, doesn't hurt to put the absolute value, so it's 5 over 12 plus absolute value of a negative value comes back as positive, and this gives us 37 over 12, and this is our total area. Okay, so if you just looked at the definite integral here, it is not fully revealing to us that we're actually finding the total area, because if you just did this part, right, it just means that you did the definite integral, but you actually took care of splitting up the whole interval into subintervals, and then looking out for portions where it's negative, and made sure that each subinterval took an absolute value of its answer, and that gave us a total area. If we didn't do that, if we did the definite integral, that will be the net signed area, then your answer would have been 5 over 12 minus 8 over 3. And that would give us a negative 27 over 12. Okay, and so you can then reduce that. It reduces by 3, isn't it? So negative 9 over 4. So you can see that it's totally a different answer. In fact, it's a negative answer. It's a net signed area. Area is coming out as negative. But that's understood in the context of net signed area. But for total area, you got 37 over 12. It's always going to be positive, the total area. Now let's do a quick look at the sketch of this graph. So our graph is y equals x cubed minus x squared minus 2x. That's your purple graph. And these were the positions where we got our zeros, right? And this region was positive, So we automatically got a positive 5 over 12. And this region here was negative and this region was negative 8 over 3, wasn't it? Negative 8 over 3. And when you take the absolute value of it, you got it as a positive, which is like flipping it to the other side of the x-axis. So you got absolute value of negative 8 over 3, which gave us 8 over 3. So I've given you some examples here, but of course it's not exhaustive. For the sake of keeping the video, not too lengthy, I am not going into too many problems, but we do have a lot of solved examples in your ebook, which I hope you'll find very helpful. So what you're going to do is practice a lot on evaluation theorem, where when you take the integral, you do the upper limit minus the lower limit, and understand now the difference significantly between indefinite and definite integrals. And the other part we saw was, other than the fundamental theorem of calculus, which was the key information here, we saw that, practically speaking, the definite integral by itself would give us the net signed area, but if you tweaked it by finding the zeros and splitting up the interval into subintervals and taking their areas, the absolute value of their areas, and then adding them up, that will give you the total area. Total area is always positive, doesn't matter if it's above or below the x-axis, but net signed area could be 0 or negative depending on which side was heavier. Like in this case, the pink portion was heavier than the yellow portion, and that's the reason why the net signed area collectively gave us a negative answer. And so it's useful in those kind of things where it gives you that information. So I hope you'll have a good time with the exercises on this, and I will see you in the next video.